Welcome to the explainer. Artificial intelligence and machine learning, they often feel like these mystical black boxes, right? Just full of impenetrable math and coding wizardry. But today, we're going to intuitively map this landscape together. We'll zoom all the way into the absolute mathematical bedrock of how a machine actually learns, understand those simple mechanics, and then zoom all the way back out to see how those exact same principles power today's most advanced neural networks. Let's dive in.
Here's our roadmap for today. We'll cover 1. The machine learning landscape. 2. The mother of algorithms. 3. Fitting the perfect line. 4. Grading the model. 5. Proving it matters. And 6. Beyond the line.
Section 1. The machine learning landscape, mapping the territory. Okay, let's start by splitting the AI world into two very distinct hemispheres, supervised and unsupervised learning. Think of supervised learning kind of like teaching a little kid. If you want them to recognize a cat, you show them dozens of pictures clearly labeled cat and maybe some labeled dog. The algorithm uses this known labeled data, the inputs like the size of the ears or eye color, to predict a specific output variable. It's exactly how an algorithm learns to predict house prices based on square footage. On the flip side, unsupervised learning is like giving that exact same kid a massive pile of animal photos with absolutely no instructions or labels and just asking them to group the photos by similarity. There's no specific truth we're trying to predict here. The algorithm is just hunting for hidden structures and clusters completely on its own, kind of like automatically categorizing your chaotic email inbox.
Section 2. The mother of algorithms, linear regression.
For today, we're going to focus on supervised learning. Specifically, we're diving into the granular mechanics of the most foundational supervised learning algorithm out there, linear regression. Seriously, if you're faced with a prediction problem, this simple, tractable, and incredibly extensible method should absolutely be the first thing you try. At its core, supervised learning algorithms really just try to determine the relationship between two variables. They want to find the function that maps an input to an output. Linear regression does this in its purest, simplest form. It basically tries to fit a perfectly straight line through your data to establish a linear relationship.
Now, what's really fascinating here is how we can look at this simple high school math equation and use it to interpret complex real-life behavior. Let's say we're trying to predict a family's weekly consumption, that's our y or dependent variable, based entirely on their income, our x or independent variable. The algorithm gives us an intercept, beta 0, and a slope, beta 1. So if we run the data and get an equation like consumption equals 49.13 plus 0.85 times income, boom, we have a highly intuitive model. It tells us exactly how sensitive our output is to our input. For every extra $100 of income, we can expect that family's consumption to increase by $85. That 0.85 is our slope. It's clean, it's interpretable, and it's super powerful. But that brings up a pretty massive question. How does the machine actually learn where to put that line?
Section 3. Fitting the perfect line, the math behind the magic. So this is where the magic happens, through a process called finding least squares. I want you to physicalize this math in your head for a second. Imagine your data points just scattered on a graph. First, the algorithm just draws an initial random line through them. Then it drops a little vertical segment from every single data point directly down or up to that line. These segments are called residuals. They represent our errors, or basically how far off our line's guess is from reality. Now we take the length of each residual, square it to really amplify those big errors, and add them all up. This gives us our sum of squared errors. Now imagine the algorithm physically rotating that line. Click by click, it rotates, recalculates all the squared distances, and checks the sum. It just keeps rotating and searching until it finds the exact angle and placement that results in the absolute smallest sum of squares. It's literally minimizing its own mistakes to find the perfect fit.
Section 4. Grading the model, measuring success.
Okay, so once the machine has spun the line around and found the absolute mathematical minimum for those errors, we have to ask the obvious follow-up. How good is our guess? Having a fitted line is great and all, but how do we quantify if it actually makes good predictions? Well, to do this, we create a baseline. We ignore our input variable entirely and just calculate the average of our output data. We measure how much all our data points vary from that simple average. That's the raw variation. Then we compare that raw variation to the variation around our fancy new fitted line.
And this brilliantly illustrates the concept of R squared. Let's say we're trying to predict the physical size of a mouse. If we just guess the average size, we're going to have a lot of error. But if we input the mouse's weight into our linear regression model, the variance plummets. If our r-squared value is 0.60 or 60%, it means that knowing the mouse's weight completely explains away 60% of the variation in its size. That is a massive reduction in variance. The closer that number is to 100%, the more perfectly your input predicts your output.
Section 5. Proving it matters. Statistical significance.
Now we have to be incredibly careful here and pivot to the very real danger of random chance. Why does this matter? Because a line that looks highly predictive could actually be totally meaningless. So the crucial point is this: linear regression is greedy. If we try to predict mouse size by adding mouse weight, tail length, and, I don't know, the mouse's astrological sign, the algorithm will try to use all of it. Now, the math is smart enough that if tail length doesn't help at all, the least squares method will just multiply its parameter by 0, effectively ignoring it. But because of pure random chance in your dataset, maybe the small mice just happen to be Capricorns, the algorithm will see that, reduce the sum of squares, and artificially improve your r-squared value. The more silly, useless parameters you add, the more opportunities you create for random events to trick your model into looking way better than it actually is.
So, to protect ourselves from being fooled by the astrological sign of a rodent, we need a statistical BS detector. We need a p-value. First, we calculate something called the F-statistic, which is simply the variation our model successfully explained divided by the variation our model could not explain. If our model is truly good, that explained variation is going to be huge, making the F-value very high. We then plot that onto a distribution to generate a p-value. This mathematically proves that the relationship we found is statistically significant and not just some random fluke of the specific data we happen to collect. You absolutely need both: a high r-squared to show a strong relationship and a tiny p-value to prove that relationship is actually real. Section 6. Beyond the line. Scaling up. We've mastered the foundational line, so let's zoom back out and see how this builds into the broader AI landscape. Because almost all the incredibly fancy machine learning algorithms you hear about, they're really just extensions of this very simple idea we just learned. For example, if you need to classify something, say, is this email spam or not, you can't exactly use a straight line. So logistic regression warps that straight line into an S-shaped sigmoid curve to give us probabilities, like, say, an 80% chance it's spam. Support vector machines, or SVMs, take our 2D line and push it into high-dimensional space, drawing complex 3D boundaries called hyperplanes to separate data, using some clever math called the kernel trick to implicitly engineer new features. And if you have way too much data, principal component analysis, or PCA, steps in and reduces dimensionality by combining features. And then there's the reigning king of AI, neural networks. A basic single-layer neural network is essentially just a multi-feature regression task. But when you add hidden layers, it automatically performs massive implicit feature engineering. It doesn't just look at pixels, it combines them into lines, then circles, then a face, layering regression upon regression upon regression. But at the bottom of the whole shebang, it is still minimizing errors to find the best fit. So we've traveled from the simplest straight line all the way to deep learning neural networks together. It's kind of amazing to realize that these algorithms aren't magic, right? They're just elegant mathematical search engines looking for relationships, rotating lines, and minimizing errors. The entire world of artificial intelligence is built on these bedrock principles. So the only question left to ask is, now that we understand the mechanics, which algorithm will you choose to uncover the hidden stories in your own data? Thanks for exploring this with me today on The Explainer.